Hello, everybody, and thanks for the invitation. Today, I will give the presentation keynote for this big data analysis and cross-layer optimization for communication caching and the computation network. And this is a work supported by National Science Foundation and also worked by my previous visitor and student, and this is here. Thank you very much. And here's the outline. Firstly, we have the introduction and motivation for 3C network. Then we try to study the 4 different scenarios over the network virtualization, D2D, mobile social network, for computing, and deep learning. Finally, we have the conclusion. So for 5G, they have typically they have 3 kind of characteristics. The first one is connected everywhere, like the IoT, so it will be improved by MMTC. And the second one is a high data rate at the edge, which will improved by EMBB. And finally, they have the ultra reliable low latency communication, URLLC, which can fit the network, unmanned driving, and so on. However, unlike this previous 2G, 3G, 4G, they have a unique modulation method. For 5G, it's more look like a buffet. So it's a assorted of different technology like the massive MIMO, D2D, ultra-dense network, everything together to achieve the 5G requirement. And here we talk about one of them, which is called communication caching and computing together. And traditionally, for them, for this network, they have this transmission burst rate, burst data, and then they have the high end-to-end latency, and then they have the backhaul burden. And in order, and for the new network, they have this kind of enhanced mobile user devices, and also they have connection everywhere, and then also they become connection-based service than the content-based service. So this will motivate this putting the caching and the computation together into the network for the reduce resource state, reduce access, storage, and the computation together. So this will actually work together. So this motivates us to use a 3C network, communication, caching, and computation. Sometimes they call it the 4C network with control. But as a matter of fact, control is just optimized of these 3 components. So 3C and 4C is a similar story. And here I just give you a very quick motivation due to the time limitation. And then let's quickly go to this detailed examples. The first one is, for this kind of big data analysis. The first one is network virtualization or network function virtualization. So in old time, we will access the network through the access point and then go to the backhaul and then internet to the destination. But in the future, when we try to implement some function, we will have this kind of network virtualization or network function virtualization. So everything is virtualized. And in order to implement one task, we will ask resources on the network. And so that we implement those ones through the different virtual machine. And for the other network, we will implement through the other side of virtual machine. So everything is controlled by this kind of software-defined controller. So by doing this one, we have reduced the expenditure, accelerate time to the market, and deliver agility and flexibility, which is a great thing. But on the other hand, in order to implement any task, we need to do a complicated optimization. And let's give you an example for that. So suppose this is a very simple problem formulation. Here, the delta means one specific task is implemented by a certain virtual machine. And this is a number of instants. And then we have this cost, like the traffic cost and the total cost. And also the traffic on it is a continuous variance from 0 to a certain maximum number. So the overall goal is to minimize certain kind of cost under many kind of constraint, which is posted in the network. And we can see that, this is a mixed integral programming because we have integral part and also continuous part. So this problem is typically NP hard. And also for the big data network, like the communication 3C network, virtualization network, this problem can be a very problem. Moreover, in order to solve that kind of problem, we don't want the problem to solve in a central place. Suppose we have a supercomputer which can do it, But there are also a problem. The problem is that, okay, you need to ship all the data to the central controller. This will cause a lot of signaling and bandwidth for the communication, and which will be inefficient. So what we want to do is that, okay, we want to divide the burden of the communication into the different parts. And some part is implemented by the SDN controller, some part is implemented by the virtual machine distributed. And in between, there are only very few kind of interaction among each other. So this one will kind of, our ultimate goal for that. And to implement such kind of goal, let's give you an example. The first one is a kind of, here we use a very simple example for the mixed integer linear programming. For other things can be extended in a similar way. Here we try to minimize a kind of linear optimization where x is integer, y is continuous, and the objective is coupled, and also the constraint is coupled. And to implement that kind of things, we use a bundle decomposition. So we divide the integral part with the continuous part. And for integral part, we try to solve the first problem. And here, plus alpha. So alpha, we assume is a bound for this continuous part. And then here, the first problem we try to solve is a pure integral programming problem. We can solve it by branching about, knapsack, whatever. Then we can solve it. And after that, we put the integral result here, and then we try to solve the continuous optimization for the variable y. And this one, we can solve it using any convex optimization and also all kinds of problem, all kinds of solution available on the market, and then we can try to solve it. And after that, we solve the integral part and the continuous part. After that, we want to see whether or not this is optimal or not. And here we have the upper bound. This is the integral part result. This is a continuous path result. And this is the upper bound. And on the other hand, by using the continuous part can provide a lower bound. And then, okay, lower bound by using some kind of Lagrange multiplier duality. And then we can easily get a lower bound for solution. If the upper bound and lower bound is close enough, we stop. Otherwise, we continue. And in the next round, instead of asking this kind of integral part to solve again, we add an extra bound, which is called bundle cut. So this bundle cut is obtained by the previous round of continuous optimization, and it has Lagrange multiplier. So after that, we have a cut to the feasible side of the integral optimization, so that, okay, the overall kind of feasible side becomes smaller. And then the problem to set to solve this integral programming becomes smaller. And then by doing this one, we can reduce the dimension. And then we do this kind of a we do this continual path again, and then come back to the master problem of this kind of, integral programming again by using the extra bundle cut, so iteratively. So the overall, this kind of geometric interpretation is like, this is the overall solution. And this is the first round. We find the feasible set here. And this is the first point of this first round of the result. And then by using the bundle cut, any feasible solution in this region, in the left lower region, below this red line, is a disappear. We don't, in the second round, we don't need to calculate. And then in this is the second round, we have another cut. So anything below, we don't need to calculate, and so on. And then, okay, we have the upper bound and the lower bound. If the upper bound and lower bound is close enough, then we stop calculation. So we found that by doing this one, we divide this kind of original problem of the integral problem and the continual problem into the two parts. For integral part, we can put into this for integral part, we can put into SDN controller. For continual part, we put into the virtual machine. And then the overall problem look like this, algorithm look like this, solving the master problem and for the integral part, and then we solve the sub-problem for the continuous part, and then we see whether or not we should terminate. If not, we add the bundle cut again and to the master problem, so the master problem becomes smaller, and then iteratively until we satisfy. So here, okay, you can see the master problem is solved by SDN, and then there's a sub-problem which is solved by virtual machine. However, there may be multiple virtual machines, and we want to divide the subproblem into the multiple virtual machines. So how could we do it? So here we try to use this alternative direction method of multiplier, ADMM, to divide the continuous problem into multiple problems. Here we have an example, again, it's linear programming. Suppose we minimize hy under the constraint of dy equal to c. And if we're lucky, okay, the objective function can be divided. So y is a huge vector. And then we can divide the y into x and z. We divide into two parts. And then we're lucky to find that the objective function can be decoupled, and also the constraint also can decoupled. So if we can do this one, and then we can formulate the Lagrange multiplier. This is the objective function. The second term is this kind of Lagrange multiplier. And then we have the augmented one. So we add a quadratic penalty. And after that, we can ask this the first part, x part, to solve regarding z as fixed, and solving the z part regarding x as fixed. And then after that, they exchange the Lagrange multiplier. And then after that, they do the average. And after average, they broadcast the Lagrange multiplier back again. And then, okay, x can solve based on the average Lagrange multiplier from the last round. And z can also do the same. So by doing this, x1 do not kind of need to exchange the information. And so to understand this one, you can understand in this way. For example, we all know that California and Texas are two countries. Okay, one is far left, one is far right. Okay, and then the California cannot control the Texas one, and Texas cannot control the California one. But then there's a U.S. Congress. So what is the U.S. Congress? It's based on the population of the state. They have the senator and the congressman there, and then they do the vote. After vote, they have the one is far left, one is far right. After the vote, they have the direction into the middle. And this direction will influence the next round kind of decision making. So you can see that, okay, by this simple kind of, Lagrange multiplier, and we don't need to exchange all the information between the two virtual machines, X and Z. And then also, okay, they can use a very limited signaling. So this signaling at lambda, in this case, is equal to only two information. And then they just can exchange an average and broadcast back. So this will reduce the signaling a lot, while all the tasks can be solved distributed. And also, such kind of ADMM can be implemented in a distributed way by using the Hadoop. And MapReduce Hadoop is you can consider is a map as a virtual machine for the different subproblem. And then Hadoop is basically average. And then this iteratively will solve this kind of bundle decomposition as well as the ADMM together. So the proposed algorithm can also solve in the big data platforms. And here we set up a small platform for this kind of a different virtual machine, 80 virtual machine, and we show that, okay, for centralized solution, the complexity increase. Well, for this kind of distributed one, the scalability is almost flat. So this is by real hardware implementation in our lab. And this is the first topic. The second topic is regarding the social network for D2D. So for this kind of device-to-device communication, is this kind of 4.5G or almost 5G solution. So the device can, in the physical layer, can exchange the information. On the other hand, the social network on the top layer, and they can consider this kind of social relationship, and also, they can exchange the information by helping each other. And for the physical layer, okay, they are nearby, and then they can also do this power control, co-channel interference to improve the performance. However, these two need to match together, and the people next to me might not be my kind of friends, and my friends may be far away to each other. So those things need to match the resources with different people, different demand. So this will become a matching problem. And Okay. For matching problem, the different spectrum with a different user, this matching is typically can be solved by Hungarian method. However, the Hungarian method is a complexity of n to the power 4. So it's not fit for this kind of big data, especially n increase. So in order to overcome this problem, we propose something based on the game theory, matching game theory. And there are many different types of matching game. And here we use a very simple example on this kind of stable marriage. And so we have a set of agent, man and woman. Each one will have a preference list. And then this man prefers this woman to that woman. Okay, for example, and vice versa. And then we have this blocking pair. The blocking pair means a man prefers a woman and is his current partner, and a woman prefers man to her current partner. So obviously, they will both divorce and then get remarried. So we want to have this kind of a stable matching that there's no blocking pair together. So this is the goal. You can see the matching game is not the goal of optimized network performance, but instead is try to have the stable marriage. And however, because each user try to each one onto the matching on top of his preference list. So the stable matching, even though it's not kind of optimal, but it's near optimal. Yeah, and also due to the Gale-Shapley algorithm, the complexity is O(n). And moreover, for your preference list, you only have the preference list that is close to each other. I mean, to find the people who is related to you. So the preference list can be much shorter than the number of devices. So in other words, the Gale-Shapley algorithm worst case situation is O(n), but in practice is O0. So you can see, okay, the overall, the matching game provide a kind of a near optimal, very low complexity solution to solve the matching problem. Compared with the optimal solution, which is O(n) to the power 4, it will have a huge advantage. And also it can be implemented in a distributed way. But here I show you an example. For example, Adam have this preference list. He prefers guitar most, so begin to date guitar. And Bob have this preference list. And then begin to date Irina, and because Irina is on his top of the preference list. And the cars also like a guitar most, and then cars try to PK Adam. And the guitar think car is more handsome, tall, and rich than Adam, and then damn Adam. And Adam have to find the second top on his preference list. And David do the same thing, PK Bob, and Bob have to go to a friend. So you can see very quick, okay, they can reach a stable marriage. And then the complexity is very low within very short period of run. And okay, so this is a basic matching one. And the next one, we try to talk about this forComputing. And with the Internet of Things, there are a lot of big data. And then we need a lot of computing and storage. So in this case, we need a cloud computing. And however, for cloud computing, the problem is that, okay, it's too far away. It have to interplace with cold and hydro dam, so that they don't need the air conditioning, and also the electricity is cheap and typically far away. And however, this round trip delays cannot be acceptable. So that's the reason we have the forComputing or edge computing. And in this case, we have the competition. So we have a data service operator like the cloud computing and forComputing on the top. They will compete each other for this customer. On the other hand, on the bottom layer, we have the authorized data service subscriber, and then try to subscribe for the different data service operator. And among ADSS, also have competition. Between the DSO and ADSS, they have the competition. Among this DSO, they also have the competition. So the key question is that how could we formulate this kind of a game for this two-layer case between the DSO and ADSS? So here we have a large network of fortnight network, we have the different competition between DSO and ADSS. Then we try to propose an algorithm, framework called EPEC, Equilibrium Program with Equilibrium Constraint. And this one can be calculated by ADMM as well. So let's see the example. Here is a recap. And we have this kind of a DSO on the top, try to sell the service of computing, and we have ADSS below, try to request for this one, and they have the competition. And in the classical kind of game theory, we only have one leader, one DSO, and multiple follower, multiple ADSS. And this can be calculated by cycle of the game. However, they need to have the equilibrium on the bottom to get a hollow form and put on the top, which is very limited in practice. So here we can make it more general. So suppose this DSO, we try to maximize the utility function. The utility is equal to the revenue minus the cost minus some kind of operation cost. And then for ADSS, is equal to this revenue minus the payment. And then for each DSO with a limited constraint, they want to maximize this kind of profit. On the other hand, for ADSS, it's similar things. So, they want to maximize a payoff under certain constraint. So you can see on the top, we have a multiple I because we have a multiple DSO. In the lower layer, we have the multiple J. And moreover, if suppose the upper layer is fixed, then the lower layer, based on the upper layer result, they will have a competition and it will converge to a certain solution. And this solution will fit into the upper layer part. So this will make the problem interesting. So overall, we can form the EPEC solution. So this is the upper layer for DSO. We try to maximize under its own physical constraint. And also under the constraint that this is a optimal convergence result from the lower ADSS solution. And so this lower ADSS solution will put into the upper one as a certain consideration. And also for upper one, we have a different I to compete with each other, different DSO compete with each other. So this one is an optimization within another optimization. So this will make the problem very, very interesting. And this is very good to quantify the two-level hierarchical optimization problem. And also that kind of problem is typically analyzed by the quality variation inequality. And which you can see our reference for the result, for the analysis. And here we show you the result by calculating using the ADMM. This is the number of ADSS for data center only, cloud and fog. Together, and the overall performance can be increased. And finally, we talk about the deep learning and analyze. There are many deep learning. So here we try to analyze this reinforcement learning. The so-called reinforcement learning is that, we have the keys at the beginning, and then we try to learn how to the effective and efficient method so that we can become an expert. So this is the reinforcement learning. So let's give an example. And suppose, we want to submit to the WCNC kind of deadline next year. Sorry, I should update here, And then from today, I can ask my student to go to this, work or go to have fun. If they go to fun, they will have the payoff 1. Otherwise, if they go to work, they will have the payoff 0. And anytime you go from the work to fun, they will have 1. Otherwise, they have 0 until the end of the deadline. And after deadline, I will say, let's have the fencing event. If you submit the paper, you will have fun. Otherwise, you fence with me, and I know how to chop you into pieces. So in this case, for any myopic, starting from today, they will select this kind of have fun. They will not go to this work. And then, such kind of a problem can be quantified into this payoff table. And this is a reward of the state and action. And this is different state and this different action. So this matrix basically quantifies the graph before. And what we want is that, we want to take the action such that, we want to maximize the current payoff plus this discount factor of times the future payoff. So your current action is not only good for your current payoff, but also for the future one. So if you consider the future, then things change. So for example, for this case, if you consider the future, you worry about the after the deadline, you will chop by me by pieces, then you'd better work from this way. So from today, you are starting work and until you submit this one. So this is the result. And this is from theory. And in reality, none of them submit a paper. So I have to kill them all. I'm just joking. Okay, and then, okay, how could you know about the future payoff? How could you know your current action to the future payoff? And this is typically used for this kind of, neural network. By neural network, you can calculate this Q function or the future function. And then, okay, you take the action. However, such kind of iteration can take millions of steps to converge. So what they do is that, okay, they have the actor critic. So basically, okay, actor is still the original kind of neural network for action. The critic is basically look like an advisor. Okay, try to tell, okay, if you take this action, okay, if you go out, what's the consequence? So instead of asking go out, the actor will train himself. So why it's called actor critic? Because for moving, and you only have once for release. After release, if even though you know something wrong, you cannot correct it. But if before you release, if you talk to the critic, and then the critic can give you the feedback about potential audience response, and then you can edit in your movie to change the result. So that's the reason it's called actor critic result, to reduce this kind of number of rounds for the interaction to the environment. And also that such kind of things is using the AlphaGo 0, which self-learning, and AlphaGo is just a kind of supervised learning. It's a good student of human, and which can beat the human. However, for AlphaGo 0, it's just self-learning. Nobody teach it. And after 2 days of self-learning, the AlphaGo 0 beat AlphaGo 100 by 0. Okay, and finally we have the conclusion, and communication, caching, and computation are the potential solution to achieve 5G. Is only one of them. And the challenge is how to write a utility function to link the communication, caching, and computation. In the old time, okay, communication is communication, caching is caching, computing is computing. And now how can you link them together, especially for some kind of application like unmanned driving? And then after that, how could you design the algorithm to fit the network topology? For example, for this kind of bundle decomposition virtual machine, we want the SDN and the virtual machine to separate to solve their problem, and in between the signaling is minimized. So when we have to find the algorithm, we have to consider the network structure. Not like just from the textbook, we find a kind of solution and then try to implement. We have to find the way to fit where we can calculate them to reduce the signaling. So this is a very challenging part. And then we talk about the 4 different scenarios: network virtualization using the bundle decomposition and ADMM, mobile social network over T2D based on machine game, EPEC solution, and deep learning. And finally, okay, allow me to do an advertisement. And we are in the University of Houston, and there are many interesting activities available. And if you want to pursue the PhD study, and we have the pension and the tuition. And if you want to visit us to collaboration, you are quite welcome. And I'm sure that you will have a great fun here. Okay, thank you very much. Appreciate it. And if you have a question, okay, please email me, and you can Google my name and you can find my email. Thank you very much.